Welcome to this explainer for the foundations of General Emergence Mechanics. Let's dive right into Episode 9, the birth of GEM and the three axes of persistence. Over our previous 8 sessions, we've carefully mapped out the mathematical groundwork for stability and coherence. But today we step into an entirely new domain. So, I invite you to settle in and focus. We are about to shift gears. We're no longer just observing static systems in a vacuum. We're learning the fundamental, dynamic language of how they actually endure over time and under stress. Here is our roadmap for today. We'll start with the limits of admissibility. Then we'll break down our 3 new axes: depth, stiffness, and viscosity. After that, we'll see what happens when we combine them. And finally, we'll arrive at the true birth of GEM. Okay, Part 1. The limits of admissibility, and why we need to look beyond local mechanics. To really appreciate where we're going, we have to reflect on our journey so far. There's a critical conceptual gap we need to bridge today. You'll remember that modal theory gave us local phase minima. It gave us the math to determine what's locally stable in total isolation. Then the Global Coherence Framework, the GCF, stepped in to provide a global filter, mathematically showing us if a structure is globally admissible within a wider system. And that was a huge, necessary step forward. But admissibility alone is, well, fundamentally incomplete. A structure might be admissible in theory, but that label doesn't tell us what happens when the physical environment actually pushes back. Right now, we lack the mathematical framework to describe how a state survives active stress, how it resists continuous deformation, and how it recovers when that stress is removed. Without that, we only have a snapshot. What we're missing is the language of persistence. So let's build that new geometry, starting with our first axis, depth. What exactly is depth? Well, it's the measure of how difficult it is to dislodge a structure from its persistence basin. Think of depth as a system's core, absolute resistance to total collapse. It asks a very specific physical question: exactly how much energy is required to force the system entirely out of its current state into a completely different phase. This is the foundational metric of survival. If you picture a system as a fortress, depth is the height and the sheer density of its outermost walls. Visualize a deep, topological basin versus a shallow one. A structure sitting at the bottom of a really deep basin has incredibly high retention. It's robust against perturbation because any attempt to push it out means climbing a massive energetic hill. A shallow basin, on the other hand, requires very little energy to escape. A slight mathematical breeze, metaphorically speaking, could just push it over the edge into total collapse. So a deeper basin provides that crucial retention, making a state significantly harder to dislodge, even under extreme stress. That sheer difficulty of escape is our first axis. Right, moving on to our second axis, let's talk about stiffness and resisting deformation. While depth tells us about the energy it takes to escape the basin entirely, stiffness tells us what happens inside that basin when the system is actively provoked. Stiffness is the measure of how strongly a structure resists deformation away from its ideal, preferred configuration. If depth is about retention, stiffness is about pattern rigidity. It's the restoring strength. It's a measure of the system's absolute stubbornness to maintain its exact internal shape when it's under immense duress. Think about the restoring forces at play here, the actual topological curvature of the basin itself. A stiffer structure has a steep, sharp curvature around its local minimum. When it gets pushed, it doesn't just slide smoothly up the walls, it vigorously, almost violently, resists being bent away from coherence. It fights back with an immediate opposing force. A system with high stiffness refuses to be warped. It demonstrates a powerful, immediate memory of its preferred configuration, even when displacement forces are trying to pull it apart. Which brings us to our third and final axis, viscosity. It's all about time and recovery. This is where things get truly dynamic, because we are incorporating the dimension of time into our framework. Viscosity measures how a system relaxes, recovers, or lags under disturbance over time. It's the time-dependent resistance to rearrangement. See, we can have a structure that's incredibly deep, and we can have one that's highly stiff, but how quickly does it actually respond when those properties are repeatedly tested? Time is the invisible variable that dictates the true survivability of the system, especially in an environment where disturbances aren't just singular events, but continuous sequences of stress. Consider what happens after a system is struck. A highly viscous system retains a deep memory of that damage. It lags. It exhibits what we call hysteresis, meaning its path to recovery is slow, delayed, and heavily dependent on its past states. It takes its sweet time settling back into its ideal minimum. Conversely, a low viscosity system recovers almost immediately, just snapping right back into place without a lingering memory of the disturbance. Viscosity completes our mechanical picture by describing that temporal behavior and the recovery time under ongoing stress. Okay, we have our three axes. Now let's look at combining them into a structured balance. This is really the conceptual climax of today's lesson. We have to bring these isolated axes together into a single cohesive geometry. Let's look at what happens if we isolate them, just to understand why we need all three. Step 1. A system might have tremendous depth, but without a quick recovery, without the right viscosity, repeated minor stresses will just accumulate, eventually destroying the system before it can relax. Step 2. A system might be incredibly stiff, violently resisting bending, but without the robustness of depth, a single large shock will snap it right out of its shallow basin. Step 3. A system might have high viscosity, relaxing slowly, but without strong retention, it'll just inevitably drift into permanent collapse. Mathematically, no single axis is enough on its own. So the crucial takeaway here is this. Persistence is not a single number. You can't reduce it to one dimension. It is a structured balance. It's the continuous interaction of retention from depth, resistance from stiffness, and recovery governed by viscosity. Only when these three properties are bound together do we actually have a rigorous definition of something that can endure its environment. And that profound realization brings us to part 6, the birth of General Emergence Mechanics. This is where it all comes together. A persistent state is structurally mapped as a simple coordinate triple, d, k, and v. Depth, stiffness, and viscosity. Now, we aren't going to get bogged down in heavy derivations today. Just let this conceptual equation anchor our new mathematical reality. GEM formally begins the moment we stop asking, what is locally stable in a vacuum, and start describing complex structures within this exact coordinate system. We define them simultaneously by how hard they are to leave, how strongly they resist distortion, and how they lag and recover through time. If we summarize our entire journey up to this exact moment, modal theory initially gave us the local phase structure. Then the Global Coherence Framework gave us the global admissibility filter. But now, with the birth of GEM, persistence itself finally becomes the primary structural object that we can mathematically measure. GEM is far broader than just phase selection. It moves us out of static observation and right into the dynamic geometry of survival itself. Before we finish up, I really want you to ponder the geometry we've just built. Think about it. Is a missing axis stable? Or is it only incomplete? If a system has depth without stiffness, or stiffness without viscosity, is it actually stable, or is it just waiting for the exact right frequency of disturbance to tear it apart? Think carefully about how a system relying on just one or two of these pillars would inevitably face a stress it simply cannot survive. A system does not persist for one reason alone. It persists because retention, resistance, and recovery form a geometry together. Next time, we ask how that geometry can be scored and how it fails.